IBESS, Investigating Ecosystems Part 1, is the first of two movies covering Topic 2.5 in the ESS syllabus. These two movies focus on the techniques for measuring ecological components, both living and non-living. Part 1, this movie, introduces and evaluates various sampling techniques. The essential ideas are: the description and investigation of ecosystems allows for comparisons to be made between different ecosystems and for them to be monitored, modeled, and evaluated over time, measuring both natural change and human impacts. The second essential idea is ecosystems can be better understood through the investigation and quantification of their components. Here is the outline of the two movies available in the Topic 2.5 Investigating Ecosystems series. Use this outline to find the movie you need for review. This is Part 1, examining dichotomous keys, probes, quadrats, and various sampling techniques. Here is the first IB syllabus statement of the movie. The study of an ecosystem requires that it be named and located. For example, Danikerwald in Bar, Switzerland, a mixed deciduous coniferous managed woodland. The study of an ecosystem requires that it be named and located. For example, Madre de Dios, Amazon, Peru, Tambopata National Park, a tropical rainforest. The study of an ecosystem requires that it be named and located. For example, the Appalachian region, Pennsylvania, United States, a temperate managed grassland. Here is the next IB syllabus statement. Organisms in an ecosystem can be identified using a variety of tools, including keys, comparison to herbarium or specimen collections, technologies, and scientific expertise. And remember, when constructing identification keys, students should be reminded that generic terms, such as big or small, are not useful. Comparative quantitative descriptors and simple identification of the presence or absence of external features are most useful in keys. Here is an example of a key, a dichotomous key. Dichotomous, two choices at every step. Pay attention, two choices at every step. Start with an unknown organism to identify and ask, does it have feathers? Yes or no? Does it swim? Yes or no? Or does it have legs? Yes or no? For example, starting with an unknown organism. Feathers? No. Legs? Yes. Lizard. The unknown animal is a lizard. Avoid using vague terms such as large or small, dark or light when constructing simple identification keys. Here is a dichotomous key structured in a linear fashion. I prefer the linear approach to constructing dichotomous keys. Let's attempt to determine organism C as our unknown organism. And we start at 1 with two choices, A or B. Wings are covered by an exoskeleton, or wings are not covered by an exoskeleton. Not covered, so we go to 3 as instructed. Wings point outward from the body, or wings point toward the rear of the body. The wings point outward, so our organism is a dragonfly. Note, in constructing keys, avoid using vague terms such as large, small, dark, light, etc. Here is a linear dichotomous key. Pay close attention because you need to be able to construct a key. Let's identify organism X. Beak, long, slender, or beak, stout and heavy. Stout, heavy, go to 2. The bottom surface of the lower beak is flat, straight, or the bottom surface of the lower beak is curved. It's curved, go to 3. The lower edge of the upper beak has a distinct bend, or the lower edge of the upper beak is mostly flat. It has a distinct bend. Cameranchus is our organism. Here's a chance to practice. Construct a key to identify the 6 organisms in Figure 1 by their visible physical characteristics in the diagrams here. Note, avoid using vague terms such as large, small, dark, light, etc. For example, you cannot tell from the diagram that the alligator is larger than the frog. You cannot tell from the diagram that the snake has rough skin and that the frog has smooth skin. Use visible characteristics. Assume nothing. Turn the movie off now and get to work. Here is my dichotomous key from Figure 1 on the previous slide. Other keys are possible. In other words, yours does not have to be identical to this one. Take some time to compare your key and this one. But remember, your key should have no terms such as large, small, dark, light, rough, smooth, all of which cannot be determined from the diagram on the previous slide. Now, if you have an unknown organism in the field and you do not have a key, you could use herbarium specimens or photographic guides, or you could use the knowledge of experts, or you could use some technology, for example, apps that provide field information. Let's move to the next IB syllabus statement. Sampling strategies may be used to measure biotic or abiotic factors and their change across space. The design of sampling strategies needs to be appropriate for its purpose and provide a valid representation of the system being investigated. Suitable sampling techniques include random or systematic techniques in a uniform environment or transects over an environmental gradient. Most abiotic variables, non-living variables, are measured using probes. There are pH probes, temperature probes, nitrate, phosphate probes, metal probes, turbidity sensors, and light probes, and one could use a rain gauge to measure rainfall. This basic method applies to most, if not all, field investigations, whether measuring the non-living, the abiotic, or the living, the biotic. The sample locations should be selected randomly. Record data from many samples and state what it is that you are recording. Be specific. What is being measured? Calculate averages. Samples should be taken over the entire year so that you can determine whether there are seasonal changes. And lastly, multiply up to estimate values for the larger area. You should be familiar with the measurement of at least 3 abiotic factors, and these factors could come from different ecosystems. The marine ecosystem, where you could measure salinity, pH, temperature, dissolved oxygen, or wave action. Freshwater ecosystem, you could look at turbidity, flow velocity, pH, temperature, dissolved oxygen. Or the terrestrial ecosystem, temperature, light, wind speed, particle size, slope, soil moisture, drainage, or mineral content. A wide range of parameters can be used to directly test the quality of aquatic systems, including pH, temperature, suspended solids, in other words, turbidity, metals, nitrates, and phosphates. And for these abiotic variables, the use of probes is appropriate. For example, a nitrate probe or heavy metal probe, or a temperature probe, or a pH probe, or the use of a Secchi disc to measure turbidity, or a turbidity sensor. Just to be clear, turbidity is the measure of the cloudiness of a fluid caused by large numbers of suspended particles that are generally invisible to the naked eye but can clearly be seen when you have turbid water. You need to be able to evaluate methods to measure at least 3 abiotic factors in an ecosystem. Some of the strengths. Quantitative measurements using the probes provide validity. Random samples are statistically valid. Many samples increase data reliability. And seasonal measurements provide information about change in abiotic variables over time. The sample size must be large, but this could be expensive in terms of time and money. Probes require regular calibration. The Secchi disc for measuring turbidity is not a quantitative measure, and abiotic variables change over time. Thus, regular samples must be taken to ensure reliability of data. Now, we've just looked at strategies for measuring abiotic factors. Now let's look at sampling strategies used to measure biotic factors. The methods for estimating the abundance of non-modal organisms, like plants, include the use of quadrats for making actual counts or measuring population density or percent cover and percent frequency. On this slide, you can see a quadrat. Get the term right. It's not a quadrant. It's a quadrat. Let's be specific. It's incorrect to use the term quadrant. The quadrat can be used to gather data such as counts of individual organisms, percent cover, population density, which is count per area, or percent frequency, which is the number of quadrats in which the species is found, divided by the total quadrats sampled. I will explain these terms in the slides to come. Randomly placed quadrats work well for sampling non-modal organisms in ecosystems without significant structural depth, such as grasslands or the bottom of a reef. Quadrats do not work well in the open ocean or for sampling migratory species. Now notice, I'm adding some evaluation of quadrats here. Pay attention. Quadrats can be large or small depending on what you hope to sample. The design of sampling strategies needs to be appropriate for its purpose and provide a valid representation of the system being investigated. Choose the quadrat that is appropriate for the ecosystem and the species that you want to sample. And never forget the fundamentals of good sampling strategy. Sample location should be selected randomly. Record data from many samples and state what it is you're recording. Be specific. What's being measured? Calculate averages. Samples should be taken over the entire year to account for different seasons. And then you multiply up to estimate values for the larger area. Quadrats in an ecosystem should be selected randomly. Data from randomly selected quadrats is statistically valid, but there are risks with randomly selected quadrats. By chance, certain species could be underrepresented in the data if quadrats happen to miss a species. As well, certain species could be overrepresented in the data if two quadrats are, by chance, next to each other. In a more uniform ecosystem, such as a grassland, quadrats could be selected in a systematic manner rather than random. Random quadrats in a structurally complex system could provide counts of individuals, 1, 2, 3, 4 of species A, and 1, 2, 3 of species B. Now, instead of counts, percent cover could be the measured variable. Percent cover is the proportion of ground occupied or covered by the projection of aerial parts of plants, parts that would intercept light. In this example, percent cover of the quadrat, percent cover of the plants being sampled, is 25%. Percent cover is the proportion of ground occupied or covered by the projection of aerial parts of plants, the parts that intercept light. You can see this well in this diagram. Now here is a 1 meter by 1 meter quadrat, and you can measure percent cover to be 50% plus or minus 10%. Now the instrument error is large, but this should not dissuade scientists from measuring in the first place. Quadrats can be large to assess large species or large areas of the habitat, or quadrats can be small depending on the species being sampled. And what is it that you're measuring? Be clear. Counts of individuals, percent cover, population density, or percent frequency. Population density is the number of individuals divided by the area, number of individuals per area. For example, if the area is 100 meters by 100 meters, which is 10,000 square meters, and your count is 100 individuals of sugar maple trees, then your density is 100 trees per 10,000 square meters, or 100 trees per hectare. Now, percent frequency is the number of quadrats in which the species is found divided by the total number of quadrats sampled. For example, if sugar maple is found in 2 out of the 8 quadrats in a forest, the percent frequency is 25%. And here is a relevant IB syllabus statement. Evaluate methods for measuring or estimating populations of modal and non-modal organisms. Evaluation of the method for biotic components of an ecosystem requires examining the specific situation. Is it a grassland or a forest, or is it an aquatic ecosystem? Is it a plant species that you're interested in, or animal? And what is the sampling strategy specifically? You've got to pay close attention to the specifics here. But don't forget the general strengths and limitations. Now, I'm not going to read through all of these statements again, except to note that I've added these statements that dry mass is more accurate than wet mass, and this is okay for plants, but that dry mass measurements of a consumer population would require the death of an animal, and this raises ethical issues. And then secondly, modal species, those that move or migrate, would require something other than quadrats, because using quadrats for migrating species is inappropriate. So let's evaluate. Using a quadrat in a uniform habitat, such as a grassland, works well. There are non-modal species here, and the ecosystem is not structurally complex. You have to ask, is the quadrat large enough for what it is that you want to study? And consider the measurements. Are you counting individuals in the grassland? This would be difficult, very difficult to count individuals in a grassland. Percent cover might be easier. In a non-uniform ecosystem or a structurally complex system, using a quadrat requires some consideration. Are you measuring the canopy species or the forest floor species? Are you doing counts or percent cover? Is the quadrat large enough for the species that you wish to sample? And consider alternative methods to the quadrat, such as aerial surveillance. Using a quadrat for open water sampling is ineffective because the quadrat has a two-dimensional quality while open water systems are clearly three-dimensional. Using a quadrat on the reef bottom is effective because the reef bottom is not structurally complex. A quadrat does not sample modal or migratory organisms well. The pitfall trap would be a sampling strategy for modal species, moving animals. But evaluation. Would a pitfall trap evenly sample all types of organisms, large ones, for example, or winged organisms? And the death of insects or animals in the bottom of the cup raises ethical issues. And don't forget the basics of sampling, no matter what measuring tool you're using. The small mammal trap, or the live animal trap, is another sampling strategy for modal species. But let's evaluate. Does the trap evenly sample all types of organisms? Nesting versus migratory, nocturnal versus diurnal. Does the experience of being trapped influence the possibility of being trapped a second time for the purposes of the Lincoln Index? Does the marking of the animal influence its survivability? And consider trap placement, trap density, relative to the natural movement of the animal. Are there limitations in sampling large animals using the small mammal trap? The camera trap is another sampling strategy, but let's evaluate. Does the trap evenly sample all types of organisms? Nesting versus migratory, large versus small, nocturnal versus diurnal. Some upsides of the camera trap is that there's no negative trap experience and there's no need to mark the animal. You do need to consider trap placement, trap density relative to the natural movement of the species. And I ask, are there limitations in sampling large or small animals? There shouldn't be, except extremely small animals like insects would be missed by the camera trap. And the radio collar is another sampling strategy for modal species. Let's evaluate. Does the collar influence the survivability of the organism? What is the weight of the collar relative to the weight of the animal? Does the collar influence hunting or reproductive habits? Aerial surveillance is still another strategy for sampling modal animals, but let's evaluate. It's a terrific strategy for sampling large areas, but it really functions for large animals only and open habitats only. Here is the last IB syllabus statement of the movie. Sampling strategies may be used to measure biotic and abiotic factors and their change in space along an environmental gradient over time through succession or before and after human impact, for example, as part of an environmental impact assessment project. Human impacts might include toxins from mining, landfills, eutrophication, effluents, oil spills, overexploitation, and change of land use, for example, deforestation, or development, or use for tourism activities. You need to be able to evaluate methods to investigate the change along an environmental gradient and the effect of a human impact in an ecosystem. This next section of the movie is about gradients and how to measure factors, biotic and abiotic, along the gradient. A gradient is a gradual change in an abiotic factor across space. For example, there is likely a soil moisture gradient from the edge of the pond to a location away from the pond. A transect line with randomly selected quadrats along the gradient could be used as a strategy to measure biotic or abiotic factors along the gradient. With a mountain or a change in altitude, we have a gradient of temperature or rainfall or soil chemistry or all three. A transect line, or in this case a belt transect, could be used to assess the change in biotic and abiotic factors along the gradient. Transect lines with sampling locations identified along the line are used to assess the change in biotic and abiotic factors along the gradient. In the upper right of this slide, we can see gradients of various types in the image. In the upper left, we can see people using quadrats along a transect line to assess the change in species, a biotic component, along the gradient. In the lower image, there are possible transect lines across the habitat that could be used to assess the change in species along the gradient. Here we have a salinity gradient across space from low salinity here to high salinity here. And we have a graph at the bottom that shows how plant species change from low salinity to high salinity. This type of graph at the bottom is called a kite diagram, and it shows the limits of tolerance for species. The phrase limits of tolerance should be familiar to you from our study of the niche ecosystem 2 part 1. In this image, we can see eutrophication along the Louisiana coastline in the United States. A transect line could be used to assess the change in the abiotic and biotic factors along the gradient from high eutrophication to low. Here are some evaluative statements. Are the samples taken at various depths? Are the samples sufficient in number? And are the samples taken seasonally? Here is an image of hot water being released by a factory as an effluent. A transect line could be used to assess the change in the abiotic and biotic factors along the gradient from very warm to cooler water. Quadrat selection along a transect is not fully random because all quadrats fall on the transect line and are not freely chosen from any location in the ecosystem. This is a limitation of quadrat selection along a transect. Here is an image of the BP oil spill in the Gulf of Mexico in 2010. A transect line, a belt transect, could assess the change in the abiotic and biotic factors along the gradient from high levels of oil to low. Quadrat selection along a transect is not fully random because all quadrats fall on the line and are not freely chosen from any location in the ecosystem. As well, are the samples taken at various depths? Are the samples sufficient in number? And are the samples taken seasonally? Here is a transect line across a deforested area. Hopefully by now you can see how a transect line can be used to assess gradients caused by human impact, whether that be toxins from a mining activity, thermal pollution, oil spills, landfills, eutrophication, effluent, or a change of land use, for example, deforestation. And don't forget that environmental impact assessments would employ effective sampling strategies to assess the impact of a development project before the project is begun. The gradient in this diagram runs from the ocean to inland. The gradient could be soil moisture or possibly salinity or even wind. Now the transect lines run parallel to the gradient, but it's always important to take many samples. As we can see here, we have many transect lines and we have many samples at each location along the gradient. Sampling could occur over time in one location to assess the impact of succession on the biotic and abiotic factors that change over time in succession. And remember, measurements should be repeated to increase the reliability of data. The number of repetitions required depends on the factor being measured. And that brings us to the end of Topic 2.5, Investigating Ecosystems, Part 1.